Welcome to Yashil Chemistry Academy, CBSE 12 Chemistry with Srinivas Vasudevamurthy. Today we will discuss about Raoult's law. In this PowerPoint presentation, we will cover the following topics. Number one, Raoult's law for a solution containing two or more volatile solvents. Raoult's law for a solution containing a non-volatile solute and a volatile solvent. Then, what is the meaning of ideal solution? Conditions for a solution to be ideal. Then non-ideal solution, conditions for a solution to be non-ideal. Then positive deviation with example, negative deviation with example. These are the things you'll be seeing. First, we'll start with Raoult's law for a solution containing two volatile solvents. Of course, two or more volatile solvents. I'm taking two volatile solvents here, right? Okay. So I have taken two volatile solvents. Let us say A and B. So I have taken a volatile solvent A. This is solvent A, pure solvent. And another solvent B here, another volatile solvent B here. Solvent B I have taken. Right? Both are pure solvents. Vapor pressure of solvent A is P naught A, pure solvent A. I have taken it as P naught A. Vapor pressure of pure solvent B, I have taken it as P naught B here. I am mixing it together to get a solution AB here. To get a solution AB. AB is the solution here. Now, in AB, partial vapor pressure of A is PA and partial vapor pressure of B in AB is PB here. AB is the solution. By mixing two volatile solvent A and solvent B, I mixed it. Vapor pressure of pure solvent A is P naught A, pure solvent B is P naught B, and in the solution AB, vapor pressure of solvent A is PA and vapor pressure of solvent B is PB here. Right. It is found out that the PA, that is partial vapor pressure of A, in the solution AB is proportional to mole fraction of A. PB is proportional to mole fraction of B. This is the determination. PA is proportional to mole fraction of A. PB is proportional to mole fraction of B in the solution here. Now let us say, look at the statement of Raoult's law for a solution containing two or more volatile solvent here. This is the statement. In a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to its mole fraction in the solution. Once again, I'll tell you. In a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to the mole fraction of it in the solution here. Right? So PA is proportional to mole fraction of A. PB is proportional to mole fraction of B here. Right? Total pressure is PA plus PB here. P total pressure of this solution I want to find out. P total is equal to vapor pressure of A, partial vapor pressure of A in the solution AB plus partial vapor pressure of B in the solution AB here. PA we already see P naught A into mole fraction of A plus PB is P naught B into mole fraction of B. This is total pressure in the solution. So this is the solution we have seen. Total pressure of the solution is partial vapor pressure of A plus partial vapor pressure of B here. Already we have seen PA is proportional to mole fraction of A. Or I can write PA is equal to P naught A into mole fraction of A. Same way, PB is proportional to mole fraction of B here. Or PB is equal to P naught B into mole fraction of B. So P total is PA plus PB, which is equal to P naught A into mole fraction of A plus P naught B into mole fraction of B here. This is the for a solution here, right? Now let us see what will happen in the vapor phase. In the solution I have seen, I'm going for the vapor phase. Right? In vapor phase, you will see what is the condition here, vapor phase. Right. Let us say in the vapor phase, I take it as mole fraction of A, mole fraction of A. I'm taking it as YA, and mole fraction of B, mole fraction of B I'm taking it as YB here, YA and YB. Now let us see how it is related. Mole fraction of the vapor pressure. YA is equal to PA by P total. Or I can write it as P naught A into mole fraction of A divided by P total. That is YA here. Same way, that is the mole fraction of A in vapor phase. YB, mole fraction of B in vapor phase. PB is equal to PB by P total. YB equal to PB by P total, which is P naught B into mole fraction of B divided by P total. This is the situation in the vapor phase. You will get numerical based on this, finding out the mole fraction in the solution as well as mole fraction in the vapor phase here. This is the equation we get in this case. This is for a solution containing two or more volatile solvents. So once again, I'll tell you the statement. For a solution containing two or more volatile solvents, partial vapor pressure of each component is directly proportional to its mole fraction. Now let us see the graph for an ideal solution or a solution containing two volatile solvents A and B here. X-axis mole fraction is given, Y-axis vapor pressure is given here. When I move from left to right, mole fraction of A is left extreme, A is 1, and mole fraction of A decreases and becomes 0 at the right here. Whereas mole fraction of B at the left extreme is 0 and it increases, become 1 at the right extreme. So at the left extreme, Y-axis, we can see mole fraction of A is 1, therefore it's a pure solvent. It's shown as P naught A here. Same way, right extreme, mole fraction of B is 1, so it is P naught B, vapor pressure of pure solvent B here. And the dotted line shows the mole fraction at different, shows the vapor pressure at different mole fraction. That vapor pressure different mole fraction is shown. And the thick line you can see that shows the total pressure, PT equal to PA plus PB. So I can find out the total pressure at any mole fraction. I can also find out the partial vapor pressure of A and partial vapor pressure of B at any mole fraction we can find out here. Right. Now, I'm going for a solution containing a non-volatile solute and a volatile solvent here. See, for example, I've taken a pure solvent here, right? Pure solvent, A is taken. P naught A is the vapor pressure here. Let us see what do you mean by vapor pressure. So I've taken a closed system here. So the liquid, this is the liquid phase. Above the liquid phase, it is, we call it a vapor phase. So liquid phase and vapor phase I have taken here, right? Now, the liquid phase, the molecules have got different kinetic energy. I look at the average kinetic energy of the molecule. Now, the molecule which has got kinetic energy higher than the average kinetic energy evaporate and move to the vapor phase here. That is called as evaporation or vaporization. Molecules having higher kinetic energy than the average kinetic energy of the system moves to the vapor phase, that is evaporation here. Then the molecules, after some time, molecule in the vapor phase condenses, move back to the liquid phase, that's called as condensation. So both take place simultaneously. Evaporation and condensation take place simultaneously. At a particular stage, rate of evaporation becomes equal to rate of condensation. Rate of evaporation becomes equal to rate of condensation. Then we say an equilibrium is achieved here. An equilibrium is achieved. Vapor pressure exerted at equilibrium is called as vapor pressure of the liquid or vapor pressure of the solvent. It's given as P naught here. So vapor pressure exerted at equilibrium is the vapor pressure of the liquid. It is equal to P naught here, right? Now let us say I'm adding a same solution I have taken, same liquid I have taken. Right? Liquid A I have taken. I am adding a solute B, a non-volatile solute. Non-volatile solute. That is, B will not evaporate. Right? I can say sodium chloride, potassium chloride. There are non-volatile solutes. I am adding a non-volatile solute B here. So AB is the solution form here. AB is the solution form. Now what happens? The solute B and the solvent A, they will interact with each other. Of course, A and A interaction is already there. B and B also will interact. Now the A-B interaction will start here. So, now the solute B interact with solvent A here in the solution. A-B interaction taking place. Because of the interaction, the number of molecule going to the vapor phase will become lesser here. The number of molecule going to the vapor phase will become lesser here. So the vapor pressure will decrease here. Now let us say vapor pressure of the solution A, B is P. P naught is the vapor pressure of solvent A. Vapor pressure of the solution containing a non-volatile solute is P. Right. So P naught minus P is called as lowering of vapor pressure. P naught minus P is known as lowering of vapor pressure. So for P naught minus P is the lowering of vapor pressure. For 1 atmosphere or 1 bar, 1 Pascal, whichever way you want to take, P naught minus P by P naught. This is called as relative lowering of vapor. Relative lowering of vapor pressure. That's what we are taking. So for a solution containing non-volatile solute, we have seen solvent, pure solvent is P naught. Solution is P containing a non-volatile solute. P naught minus P is lowering of vapor pressure. P naught minus P by P naught is called as relative lowering of vapor pressure. Now let us see the statement for Raoult's law for a solution containing a non-volatile solute and a volatile solvent. Here is the statement. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute in the solution. Once again, I will tell you. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to the mole fraction of solute in the solution. Right? Here, A is the non-volatile solute, B is the solvent. Here, A is the non-volatile solute, B is the solvent. That's what I have taken here. So I can write P total is equal to P naught A, that is solute, into chi A, mole fraction of solute, plus P naught B into mole fraction of B. Right. This is what we get here. PA equal to P naught A into mole fraction of A plus P naught B into mole fraction of B. Now, the solute is non-volatile, so P naught A is negligible because it's a non-volatile solute here. So, I can write it as P total is equal to P naught B into mole fraction of B. That is solvent here. P naught solvent into mole fraction of solvent. If you want, I can write it as solvent. If you find it easier, P total is equal to P naught solvent into mole fraction of solvent. Solute contribution is negligible. I removed it here. Or I can write mole fraction of solute plus mole fraction of solvent is always equal to 1. So I can write it as P naught solvent into 1 minus mole fraction of solute, because total mole fraction is 1 here. 1 minus mole fraction of solute. Or it is P naught solvent minus P naught solvent into mole fraction of solute here. Mole fraction of solute here. That's what we have written. I am rearranging the equation now. I am rearranging the equation. Right? So and there we have seen P total equal to P naught solvent minus P naught solvent into mole fraction of solute here. So I am writing here P total is equal to P naught solvent minus P naught solvent into mole fraction of solute here. Right, solute. Or I'm taking it to the other side, rearranging the equation. P naught solvent into mole fraction of solute, right? I'm taking this side equal to P naught solvent minus P total here. Total. Or I can write mole fraction of solute, solvent and all we can remove now. P naught minus P by P naught here. Mole fraction is P naught minus P by P naught. This is what we get in this case here. P naught minus P by P naught is the mole fraction of solute. Now let us see the statement now once again. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute in the solution. For a solution containing a non-volatile solute and a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute in the solution. That's what we got in this case here. Mole fraction of solute is P naught minus P by P naught, which is relative lowering of vapor pressure is equal to the mole fraction of solute in the solution here. Now, mole fraction of solute means number of moles of solute divided by number of moles of solvent here. Generally, number of moles of solute plus number of moles of solvent is taken as such. It will not be written as number of moles of solvent. Most of the numerical done in the CBSE textbook, even in the exam, don't neglect it. But just for approximation, we can do it. Some numerical where the solvent is very high amount, then we can neglect. But generally, it is not neglected. For a dilute solution, N solute is very small when compared to N solvent. So denominator N solute plus N solvent can be taken as N solvent here, can be taken as N solvent. Then I can write it as P naught minus P by P naught equal to mass of solute by molecular mass of solute into molecular mass of solvent by mass of solvent. P naught minus P by P naught equal to mass of solute by molecular mass of solute into molecular mass of solvent by mass of solvent. But most of the cases, better you take it as mole fraction of solute is equal to P naught minus P by P naught is equal to mole fraction of solute for a solution containing a non-volatile solute and a volatile solvent, which is equal to number of moles of solute divided by number of moles of solute plus number of moles of solvent. Right? Later on in the next class, we will do some numerical based on vapor pressure of solution containing two or more volatile solvent, as well as vapor pressure of solution containing a non-volatile solute and a volatile solvent. Right? Now let us see, compare Henry's law and Raoult's law. Henry's law gives you the solubility of a gas in the solution. That's what you have seen in Henry's law. There, partial pressure of the gas above the solution is equal to Kh, Henry's law constant, into mole fraction of gas in the solution. Here. Mole fraction of gas in the solution. As the partial pressure increases, mole fraction of gas in the solution also will increase. Here. Raoult's law, for a solution containing two or more volatile solvent, Pa equal to P naught A in the mole fraction of A here. Pa, vapor pressure of A in the solution, AB, and P naught A is vapor pressure of pure solvent A, and Chi A is the mole fraction of solvent A in the solution AB here. So Henry's law P gas equal to Henry's law constant Kh in the mole fraction of gas. Raoult's law Pa equal to P naught A in the mole fraction of A here, right? This is what we have seen in this case here, right? Now, Raoult's law becomes a special case of Henry's law when Kh and Pa are same. Kh and P naught A are same. When P naught becomes equal to Kh, then Raoult's law is a special case of Henry's law here. Raoult's law becomes a special case of Henry's law when P naught becomes equal to Kh here. That is, vapor pressure pure solvent becomes equal to Henry's law constant here. Vapor pressure pure solvent becomes equal to Henry's law constant, then Raoult's law becomes a special case of Henry's law here. Right. Now let us see, there are two types of solution we'll be studying. One is called as ideal solution, other one is known as non-ideal solution. Right. Ideal solution, we'll see solution which obeys Raoult's law over a wide range of concentration are called ideal solution. Solution which obeys Raoult's law over a wide range of concentration are called ideal solution. Of course, these two solvents should be non-reacting. Example, benzene and toluene. I'm mixing benzene and toluene to form a solution of benzene, toluene. Here, no hydrogen bond is formed, no hydrogen bond is broken here. So, no enthalpy change. Delta H mixing equal to 0. Because no bond is broken or no bond is made, no change in volume, delta V mixing is equal to 0. Interaction. Say if I take benzene, there's an interaction between the benzene molecules. Toluene, there's an interaction between toluene molecules. I have mixed together, I got a solution containing both the solvent, benzene and toluene. Now, let us say A is benzene, B is toluene, right? AB interaction in solution is nearly equal to AA or BB interaction. There's no change in the interaction here, there's no change in the environment here. AB interaction is nearly equal to AA and BB interaction. So I can write PA equal to P naught A in the mole fraction of A, PB equal to P naught B in the mole fraction of B here. It's called as an ideal solution. So what our ideal solution means? Solution which obeys Raoult's law. If you write just Raoult's law, it's not sufficient. You should mention it as over a wide range of concentration are called ideal solution. Example, benzene, toluene. No hydrogen bond is formed or no hydrogen bond is broken here. So no enthalpy change, delta H mixing equal to 0. No volume change, delta V mixing equal to 0. PA equal to P naught A in the mole fraction of A. PB equal to P naught B into mole fraction of B. AB interaction is nearly equal to AA and BB interaction. This is normally you'll get a reasoning question, assertion and reasoning question. You can expect it. They'll give a statement and then they give the reason. Whenever you do the assertion reasoning question, look at assertion separately, reasoning separately. Don't combine it at the same time. First look at the assertion separately and reasoning separately. If assertion is right, put a tick mark. If assertion is wrong, put a wrong mark. Then reasoning is right, put a tick mark. Otherwise, put a wrong mark. If both are right, then you see how they are correlated with each other. When they are correlated with each other, then you will arrive at the right answer. If you together, if you look at it, you will get a lot of confusion. First, look at the assertion. If it is right, put a tick mark. Wrong means put an into mark. Direction will be over. Reasoning, you look at it. Right, put a tick mark. Wrong means into mark. If both are right, then you see how they are correlated with each other. Then the reasoning given is correlated to assertion here. This is what we are going to check in assertion reasoning question. Now let us see for an ideal solution, two solvents A and B are taken. They form a solution AB. No bond is made or no bond is broken. We are talking about hydrogen bond. No hydrogen bond is made or no hydrogen bond is broken here. X-axis, mole fraction, Y-axis, vapor pressure. One side, left extreme, mole fraction of B is 1. Right extreme, mole fraction of A is 1 here. So left extreme, Y-axis, P naught B. Right extreme, Y-axis, P naught A here. Then we have seen how the vapor pressure is changing. The blue line shows the partial pressure of A, solvent A. Green line shows the partial pressure of solvent B. The red line shows the vapor pressure of solution AB here. Red line, vapor pressure of solution AB. At any mole fraction, I can find out the total vapor pressure of the solution. Or partial vapor pressure of component B in the solution AB. Or partial vapor pressure of component A in the solution AB. Anytime you can find out here. So this is a graph for an ideal solution. For an ideal solution, this is a graph here, seen here, right? Now let us see what do you mean by non-ideal solution. Non-ideal solution is the one which do not obey Raoult's law over the entire range of concentration of this solution. It's not obeying Raoult's law here. Either hydrogen bond is formed or hydrogen bond is broken here. That is the reason why it is not obeying ideal solution here. Say I'm taking in a binary solution of A, B. A is a solvent, B is another solvent. Mixing it together to give a solution A, B here. AB interaction is not same as AA or BB interaction. Here the interaction is different here. Environment has become different here. AB interaction is maybe more or less than the interaction shown in AA or BB, a solvent A or solvent B here, right? Here new bond is made or broken here. So delta H mixing is not equal to 0 because there is some enthalpy change. Delta V mixing is also not equal to 0 here, right? And PA is not equal to P naught A in the mole fraction of A. PB is not equal to P naught B in the mole fraction of B. This is non-ideal solution. You do not obey Raoult's law over the entire range of concentration. Either hydrogen bond is made or hydrogen bond is broken here, right? There are two types of deviation we'll be studying, positive deviation and negative deviation here, right? First, we will see positive deviation. So I've taken ethanol here, C2H5OH. It's a solvent, C2H5OH. This is a solvent ethanol I have taken. Right. So it forms an intermolecular hydrogen bonding here, intermolecular hydrogen bond here. This is one solvent here, right? Now I'm mixing it, adding N-hexane now. Yeah, N-hexane is added. Another solvent, N-hexane, is added to form a solution here. Now what happens? N-hexane breaks the hydrogen bond in ethanol here. It comes in between the hydrogen bond. It is breaking the hydrogen bond in intermolecular hydrogen bond found by ethanol here. So N-hexane, another solvent, breaking the intermolecular hydrogen bonding formed in ethanol here. So here the bond has to be broken here. To break a bond, I have to supply energy. It's an endothermic reaction. So delta H mixing is greater than 0. Delta H mixing is greater than 0 because it's an endothermic reaction. Right? Now the bond is broken. So what happens? The molecules is more free now. Molecules are more free to vaporize here. It can vaporize easily. More freely it can move now. So delta V mixing is greater than 0 because it occupies more space here because the bonding is hydrogen bonding is broken here. It occupies more space. So delta V mixing is greater than 0. Now it can move more easily to vapor phase. So PA is greater than P naught A in the mole fraction of A. PB is greater than P naught B in the mole fraction of B. Everything is higher here, so we call it as positive deviation. Positive deviation. So in a positive deviation, hydrogen bond is broken. Endothermic process, delta H mixing is greater than 0. Molecules occupy more space, delta V mixing is greater than 0. Molecules are easily moving to the vapor phase. So PA greater than P naught A in the mole fraction of A. PB greater than P naught B in the mole fraction of B here. So everything is positive here. But only one thing is going to decrease here because it's an endothermic process. So energy is absorbed from the surrounding. So system takes the energy from the surrounding. So the temperature of the solution will decrease. The temperature of the solution decreases. That's the only one going down here. Temperature decreases. Remaining delta H mixing increases, delta V mixing increases. Partial vapors of A and B also increases here. Now let us see the graph for ideal gas, non-ideal gas solution showing positive deviation. The dotted line shows for the ideal solution. The dotted line shows for the ideal solution. The curved line is for the non-ideal solution showing positive deviation. So everything you can see above the dotted line, positive deviation. Above the dotted line, we are seeing here same thing. X-axis mole fraction, Y-axis vapor pressure. Left extreme, mole fraction of A is 1, so P naught A shown in the Y-axis. Right extreme, P naught B, mole fraction of B is 1 here. How it is shown, changing is shown with the mole fraction. Dotted line for an ideal solution, curved line for a non-ideal solution. The curves are higher than the dotted line because it's a positive deviation. It's a positive deviation. Graph is very important. Sometimes I ask you to draw the graph for a positive deviation. Or in the multiple choice question, they may give 3 or 4 graphs. They will ask you which one is representing positive deviation, or which one is representing ideal solution, or which is representing non-ideal solution. Now let us see the maximum in this curve, which shows the P total. I'm taking P total, maximum in the curve. I'm going here. Let us say it's maximum here, right? This is maximum vapor pressure. Maximum vapor pressure. This point is called as azeotrope. You'll see later. This point is known as azeotrope. Maximum in the curve forms azeotrope here, right? Azeotrope means constant boiling mixture without any change in its composition. Later we'll see that in detail. So this is azeotrope here. Positive deviation we have seen. I'll go for the negative deviation. Here a bond formation, new bond formation is taking place. So I take an acetone and chloroform I am taking. So a hydrogen bond is formed between the proton of chloroform and lone pair of electron on oxygen in acetone. Lone pair of electron on oxygen in acetone. A kind of attraction developed here that results in hydrogen bond formation. So here hydrogen bond is formed here. When a bond is formed, energy is released. When a bond is formed, energy is released. Exothermic reaction, delta H mixing is greater than 0. Now, because of the bond formation, molecules cannot move freely. It occupies lesser space. Delta V mixing is less than 0 here. Delta V mixing is less than 0. And of course, now the molecule cannot move to the vapor phase easily. So, PA is less than P naught A into mole fraction of A. PB is less than P naught B into mole fraction of B. This is negative deviation. Negative deviation because of the hydrogen bond formation, exothermic reaction. So everything is decreasing here. But it's an exothermic reaction. That is, energy is given out by the system to the surrounding. So temperature of solution increases here. Right. Okay. This is negative deviation. One more example you can take by mixing two solvents, aniline and phenol here. See, for example, I have taken phenol, C6H5OH, right? Another molecule of phenol, C6H5OH, and so on here, OH. So between lone pair of electron on oxygen and a proton of phenol, a hydrogen bond is formed. This is intermolecular hydrogen bonding. Intermolecular hydrogen bonding is formed. Same aniline I am taking. This also forms intermolecular hydrogen bonding, NH2. Another aniline molecule. Right. Lone pair is here, NH2. hydrogen bonding is formed. So both phenol and aniline form the hydrogen bonding. Both phenol and aniline form the hydrogen bonding. I'm mixing both phenol and aniline to form a solution. Of course, they do not react with each other. So I've taken phenol C6H5 OH. Phenol is taken. Then I'm taking aniline C6H5 NH2 here. Aniline I have taken C6H5 NH2. Right? Sorry, NH I can write here. 1 minute. Right. Now I'm taking NH2 here. Okay. Now I've taken OH and NH2 I have taken here. Right. Now I'm mixing it together. Let us see how the bond is formed there. Right. So I've taken OH. So proton of phenol. And then aniline NH2 I have taken. Proton of phenol is there. O minus H plus here. Aniline lone pair of electron is there. Aniline nitrogen has got a lone pair of electron. Hydrogen bond formation taking place. So let's mix phenol and aniline. Hydrogen bond formation takes place between the proton of phenol and lone pair of electron of nitrogen in aniline. This hydrogen bonding is stronger. Hydrogen bond formed between phenol and aniline is stronger than the bond formed in phenol or the hydrogen bond formed in aniline. When I compare these strengths here, the hydrogen bond formed between phenol and aniline in the solution is stronger than the hydrogen bond formed by either phenol or by aniline here. So it shows a negative deviation. The negative deviation curve is shown here. X-axis mole fraction, Y-axis vapor pressure, and we have seen the dotted line shows the ideal solution. The curved line shows the non-ideal solution showing a negative deviation. It is below the dotted line here, because it's a negative deviation. I'm going for the minimum here. I'm going for the minimum now. So this is the minimum value. This forms an azeotrope here. Azeotrope. Okay. So negative deviation, everything is decreasing less here, but the temperature of the solution will increase. The temperature of the solution will increase. That is negative deviation, right? Okay. Now let's see what is azeotrope. Azeotrope are the binary mixtures. That is, I'm combining two solvents to give a mixture having the same composition in liquid and vapor phase. The composition in liquid and vapor phase is same. That's called as azeotrope. Are the binary mixtures having the same composition in liquid and vapor phase here. They boil at a particular temperature or at a constant temperature without any change in its composition. We have seen positive deviation, maximum vapor pressure. Like this, we have seen a graph like this. It goes. This is positive deviation, maximum vapor pressure. So boiling point will be minimum here. The boiling point will be minimum because boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. So the boiling point is minimum here. We'll just see once again and show you for a positive deviation. So this is what? Maximum vapor pressure azeotrope. So here the boiling point is minimum. So it forms a minimum boiling azeotrope here. Minimum boiling azeotrope. Same way, negative deviation azeotrope is minimum. You see here the vapor pressure is minimum. So the boiling point will be maximum here. Negative deviation forms a maximum boiling azeotrope. Right? Positive deviation, minimum boiling azeotrope. Negative deviation, maximum boiling azeotrope here. Example of minimum boiling azeotrope is 95% by volume of ethanol, 5% by volume of water. That is the reason why when I say I want to remove all the water, I want to get 100% ethanol, 100% alcohol by fractional distillation. I can only get up to 95% volume of ethanol here. 5% water I cannot remove here. 5% by volume of water I cannot remove because it is forming an azeotrope mixture here. It will boil without any change in its composition. The whole solution will boil without any change in its composition. It will become like a single liquid now. That is the reason why fractional distillation cannot be used to get 100% ethanol. I can go up to 95%. Then I'll add some chemicals to remove the remaining water. Some agent which can absorb water molecule. I can add some agent which can absorb water molecule to make it 100% ethanol. Then negative deviation example, maximum boiling azeotrope, 68% by mass of nitric acid, and 32% by mass of water. Azeotrope boils off with no change in its composition. Therefore, their components cannot be separated by fractional distillation. I mean, I can go only up to 68% by mass of nitric acid, or I can go up to only 95% by volume of ethanol. Next class, we'll do the numerical based on Raoult's law. Thank you. This is from Yashil Academy, given by Srinivas Vasudeva.